Looking quite good, isn't it?
Yeah, it has. We just had one outage during zip lines.
Yeah, yeah, yeah. Okay, so, right, final session. We've got two talks. One from Charles, G4GUO, who is here in spirit but not in body. And then we've got Chris, M0WLK, double LK, coming back to talk about vMix. And then at the end we'll draw the raffle that the Finningley Club are running, and that'll be it. So Charles, if you just tell us when to move the slides on, we'll do it. So over to you.
Okay, well, good afternoon, everybody. I can see you, but I can't hear you. Well, Noel asked me to do a talk, and I wanted to do it on my current projects, but he told me I had to do something about DATV Express. So we've got a few slides on Express. So if you'd like to have the first one, please. Okay, because there's a 10 or 20 second delay on the streamer. So okay, well, the first thing I did with Express, or the first thing I've done recently with Express, is to set up a little server in my shed, so that which is outside in the cold, unheated. So that when the winter comes, I'll be able to send video from the warm inside the house to the shed, and I've used it's all in the little aluminium box, the Hammond box underneath, and in there we've got an Odroid C1, which is similar to a Raspberry Pi Mark II, but I consider it a bit better because it's got it's got a gigabit Ethernet on it, for example, and it doesn't share the USB and the Ethernet connection in hardware, which the Pi does. It's about the same price, and the GPIO pins on it are designed to fit with the Pi accessories, so it makes quite a nice little thing to play with. Unfortunately, everybody else has got Pis, and they all want Pi software, but never mind. So on that, to control it, rather than using the command line, I could telnet into it and just type little commands to tell it to go to transmit and what have you. What I did was to enable the Apache web server. So it's got a web server on there, and using the Common Gateway Interface Protocol. In this case, it runs a Perl program. I can actually send pictures or send commands to the DATV Express via a web page. The thing on top is a TT S2 3200, which is a DVB-S/S2 receiver. It's supported by Linux, but the Linux driver, for some reason or other, they've set the minimum symbol rate at 5 megasymbols. So to get it to work at amateur symbol rates, you've got to recompile the driver and modify one of the files to give it a much lower symbol rate, because it checks the symbol rate, and if it's below 5 megs, it just comes up with an error message, and that's it. So anyway, next slide, please. Yeah. Okay, I'll just look on mine. This is what the very, very crude web page looks like, the configuration page running on a iPhone 5. I think it's a 5, yeah. I only got the iPhone. I don't actually have a cell phone account, but I bought an infrared camera that plugs into an iPhone, so I then had to go and buy an iPhone so I could use the camera. You can see the rather large phone. It's got the FLIR infrared thing plugged in the back of it. Anyway, this is the configuration screen. You can set the frequency, symbol rate, FEC, etc., and you hit submit. And then you have to restart the program, unfortunately, because some of the things it requires to load different FPGA code. So that's why it has to be restarted. So that's basically everything to do with Linux running on a little remote server in my shed. So the next thing is I thought, well, we'll do a similar thing, but we'll do it with Windows. So I can have the next slide, please. Now this is the same thing. It's running on a Windows computer. It just sits reading a UDP socket and then spewing it out to DATV Express via USB. It sends a transport stream to Express. Express has got all the DVBS encoding in the firmware of the FPGA. So the overhead is just basically the overhead of grabbing a UDP packet and then firing it out over USB to the Express. As you can see, it's very, very simple, and it's based on the code for the Linux version. Next, please. Right, now, Chris will explain everything to do with all of this in the next lecture, I guess, or he has done already, I should say. But this is just a very, very simple graph using Graph Studio, and you just grab vMix and via the main concept encoders, which if you've got a Halpage card, you've got on the WinTV 7 disc that came with it, and then it goes into a multiplexer and then out to the UDP sender, which then goes to the Express. The Express can either be running on a Windows machine with the previous app you saw, or it can be running on a remote Linux machine. Next, please. Like to mention that Everest F50EO has added support for Express on his little Linux program, so that you can use the MPEG-4 and the Raspberry Pi. I understand that you need to modify one of the configuration files to get it to work. I haven't actually tried it myself, but I had it reported to me on the KM streamer the other day that that is the case. I don't know whether anybody's tried it. Anyway, right, next, please. Yeah, it's all right. I'm just it takes my PC a while to decide it's going to bring up the next frame. I'm thinking of writing a little SSB application for Express, so you can transmit SSB on 4 meters through to 13 SEMS using it, because when there's nobody out on TV, you might want to use all your expensive PAs and what have you on SSB and work some of these narrowband people. You can use a standard software-defined radio. This is work in progress. I've actually got it to transmit some SSB, but a couple of days ago. But then I came across a QEX article on controlled envelope single sideband, so I may try and stick that in there. Right, next one, please. Okay, now. In the States, DVB-T seems to be very popular, and there's a lot of people run the high-des equipment, and it doesn't work too well with DATV Express. So we've been investigating this, and some of the problem seems to be due to the way USB 2 works. On average, there's enough bit rate to send the DVB-T signal as 16-bit samples across the USB, but every now and again, the USB 2 stutters, and we're getting dropouts on the DVB transmission. So I increased the size of the queue inside the FPGA. It's now using 85% of the available RAM on the chip, so I can't really go any further on that, and that appears to have improved it. Testing in here using Crazy Scan which is I think it's written by a guy in Eastern Europe somewhere, and he calls himself Crazy Cat or something like that. And anyway, this is his equivalent of Jean-Pierre's DVB-S code. It allows you to display a constellation of a DVB-T signal. It only works with about 2 particular cards, which I think are both obsolete now, and it only supports the 8, 7, and 6 meg or channel width. So it's no use for the narrowband stuff. Anyway, the long and the short of it is that while I can get it to work well on this, with the HV110, which is a standalone DVB-T receiver, it still manages to lock that up. So we've still got some work to do to find out what's causing it. I've also got a UT100D. That's a little dongle that does 2, 3 and 4 meg wide channels for DVB-T, and that seems to work reasonably well, although I've only been testing it with null packets because it's a bit of a palaver to plug cameras in and what have you when you're trying to develop software at the same time, when you've got multiple machines running. So that's my excuse. Okay, next one, please. Right, now this moves on to what we're currently looking at, or I'm looking at with help from Rob. That is using DPD, or digital pre-distortion, to try and improve the output of the television transmission. So we've made some changes to the narrowband version of Express to cope with this. Next slide, please. DPD is heavily used for long-term evolution, 4G, which is a coded orthogonal frequency domain multiplex signal, a bit like DVB-T. And there is an amateur use of it developed by Warren, NR0V, which is used in the HPSDR, and it makes that's just for SSB operation. It's not for digital television, and it makes quite an improvement. You can have a look on YouTube, and there's some examples of with and without it, and I think it makes considerable clean up to the thing. On I couldn't find any suitable information on using it with DVB-S, but on LTE, the manufacturers of the base station equipment are claiming up to a 26 dB reduction in spectral regrowth. Mind you, some of that may be advertising hype. Until we actually try it ourselves, we won't know. But just because you're pre-distorting everything digitally, it doesn't mean that you can't skimp on the hardware design. So everything still has to be designed correctly. Next, please. Right, in a power amplifier, there are basically 3 things that need to be corrected. The AM to AM linearity, that's the classic. As it goes into saturation, you get a bend in the gain of the amplifier, and that has to be compensated. There's also AM/PM, which the phase delay through an amplifier can change by a few degrees as the amplitude changes. So that needs to be corrected as well. And finally, there's memory effects. The amplifiers, because they're physical objects, their distortion can change depending on what's been sent previously. So if you're transmitting something that's got lots of pulses in it, the previous pulse has sort of warmed the die of the device up, and then when it goes to the next sample to transmit, even though it may be fairly small, the die is still recovering from the changes. So that has to be corrected as well. but that's less important. Next slide, please. So it's all right. I'm just it's gone off the bottom of my screen. Right. This is an overview, a hacked diagram. Some of it's borrowed from the internet, but all the stuff that looks a bit wonky is stuff that I've done. Basically, what you do is you take some of the output from the final power amplifier via a directional coupler, you attenuate it, and then you put it into a receiver. You also take a delayed version of the what you've transmitted, the golden signal. That's a perfect signal, the thing that you really want the guy at the other end to receive, and you compare the two and see what the differences are and make a model of the differences, and then you feed that model, that's the bit that says coefficient update, into the DPD corrector, and that will then pre-distort the signal to ensure that or to try and ensure that what actually comes out of the antenna looks as close as it can be to the golden signal that you've put in from the final filters in your DSP code. So that's what we're trying to do. I think we'll go on to the next slide because I think I've mentioned it here. Right. To begin with, I've only implemented it in the narrowband version of DATV Express because obviously it takes up quite a lot of space inside the FPGA, and to keep the price of Express down, we used a bottom of the end FPGA, so much so that the latest development tools don't support it. So I have to use an old version of the tools to develop the code. We've also only implemented the AM correction. That's the amplitude correction, not the phase or the memory at the moment, and that uses a 256 entry correction table. What it does is it takes the golden signal, it works out the amplitude by squaring the I and Q, the analytic signal, and then taking the square root, and looks that up into the table, and then applies a correction to the I and Q channels depending on what's in the table. To simplify it, I've put a ramp to do the calibration. In the initial calibration, I used a software-defined radio, a separate one, and then fed it into some software and used that to do the calculations. However, when I did it automatically, and I think Rob DTS discovered this as well, it didn't work very well. So I know Rob, to get the best results, he's done it. He's created the table manually and downloaded it. It's downloaded over the USB too. So in theory, you could update it on the fly. What the Express does is the FX2, the USB controller chip, has got an I2C channel on it, and I've implemented an I2C slave inside the FPGA, so you can talk to the FPGA as if it's an I2C device, and that way I can update the lookup table in over the I2C. Now, generating square roots, which is required to calculate the magnitude of the signal, is actually quite computationally expensive. But I actually use an algorithm which takes multiple clock cycles to calculate the square root, but it can still do it in real time. It's just delayed by a number of clock cycles. So I've also added a delay in the transmit to compensate for that. So I actually distort or pre-distort the correct symbol and not the one that's out of sync. It's very simple at the moment, but it shows that the idea has legs, meaning that it's going to work, or it should work. Right, I think we can go on to the next one now. This is the this is what my calibration waveform looks like. It's just a slow ramp, and it ramps up at the rate of the symbol rate. So the faster the symbol rate you program the thing, the faster the ramp. That allows you to set the ramp running and then alter the ramp rate depending on the symbol rate you tell it to program. So it's just a simple way of doing it. And when it drops from the maximum signal to the minimum signal at the top of the ramp, that allows, if you're using a software-defined radio that's not synchronized to the transmitter, that allows you to work out where the ramp starts in your receiver software, so you can then build a calibration table. Now, the next slide I'm going to show is of one of the Toshiba, I think it is, or Mitsubishi modules. I think it's the 2-meter one. But so if we move on to the next slide. Now, this was measured with my test equipment. Unfortunately, the signal generator only operates in 1 dB steps. The yellow line is what it should be if it was a straight line, and the blue line is what I actually measured. It's not particularly easy to see on this graph, but that graph is really an S shape, because you get some loss of gain on small signals as well as on high signals, and it's to do with the crossover in the Class A/B amplifier. I'm no amplifier expert, even though my first job was designing RF amplifiers, but I soon decided that software was easier. So, but you can see that there is quite a significant distortion in the thing, and this is just the AM to AM distortion. If we go on the next slide. Yeah, these were provided by Rob, M0DTS. It looks better than it really is, mainly because one's at 7 watts and the other one's at 6 watts. This is an example of the AM to AM pre-distortion done manually by Rob. And if you correct for the power difference, it works out at about an 8 dB improvement rather than the 10 dB improvement. I checked this on the internet, and just to make sure I'm not telling a load of rubbish, but it seems that if you increase your power by 1 dB, the spectral, the third order regrowth will increase by 3 times that, so that will be 3 dB. So every time you up your power by 1 dB, your spectral regrowth gets worse by 3 dB. So that's the reason why these things start to look ghastly quite quickly. But Rob's managed to achieve an 8 dB improvement there. The best I could ever do was 6 dBs. And that's done manually rather than doing it automatically. So if we move on to this slide, the final one in this sort of sequence, you'll see that I did a literature search. I've mentioned this before, and the best I could find was about 26 dB improvement with this is from people that flog this stuff. I did find, I think it's Maxim, do a nice little board that does this all. A lot of it's done in analog, and they do ones that cover all sorts of frequency ranges. Some of them actually cover amateur bands, but you've got to request a quote from them to get a price. And I requested a quote via their website 3 or 4 times and never heard back from them. So I thought, well, they obviously don't want to sell this thing. So, and even if you go to the suppliers, things like DigiKey, they require you to get a quote for it as well. But So that's something off the shelf that people could buy if they could get hold of these things. But that's just an aside. So what the next thing? Right, I've only got 10 minutes left, so we'll have to do this quickly. If we go on to the next slide, please. Right, so my current development environment is the following: a Myriad RF, a Zipper, a Z-Board, and Petalinux. I'll explain what each of them are. The Myriad RF is produced by a British company called Lime Micro Electronics or Microsystems or something, and it's an RF transceiver, complete transceiver. The Zipper is a development board that uses a zinc processor. Sorry, the Zipper is the interface board between the Myriad and the FMC connector, which you require to plug into the Z board. Now, this is just development kit. This wouldn't be what the final system would be like. And Petalinux is Xilinx's version of Linux. I've taken the lazy way out and used something produced by the manufacturer. Right, next slide. This is my current setup in a 19-inch rack. The bottom right-hand board is the Zipper, the Z board. The one above it is the RF board, the Zipper, and the Myriad RF. And to the left is just a computer power supply, one of those computer power supplies that takes 13 volts in and provides all the volts out you need. So next slide. This is what a close-up of the Zipper and the Myriad RF is. The Zipper is the white board, which just acts as an interface that allows you to connect the RF development board up to something else. The Myriad RF, the chip in the middle, they've dramatically reduced the price. They used to want over $100 each for the price for these chips, but you can get them for about £18 each now, the chips, and that replaces about going on for half of what's on a DATV Express board. The only disadvantage is the DACs and the ADCs are only 12 bits. So if we go on to the next slide. Okay, well, the Z board, that's the processor board I'm using. That has a dual-core A9 ARM device running at 866 megahertz. Each of the processors has a Neon coprocessor, which can be used for MPEG encoding, etc. It's got gigabit Ethernet, 85,000 logic cells, and 220 DSP slices. The DSP slices are the multiply and accumulates. They're the bits that you need to do all the filtering. And because the silicon for the ARM cores and the FPGA are on the same chip, there's a very high-speed communication in the tens of gigabits per second between the two. So you don't need to worry about slow gigabit Ethernets or USB 2 or USB 3, etc. So it is quite a step up in performance. Next slide, please. Here's a quick overview of the RF devices available from Lime Microsystems. The one I'm using is the LMS 6002D, which goes from 300 megs to 3.8 gigs. They've got a much more expensive one, which they still want over $100 a piece for the chip, that goes from 100 kilohertz to 3.8 gigahertz. And sometime in the future, they've got this marvelous LMS 8001 chip that will go from 100 kilohertz to 12 gigahertz in a single chip. So that's basically, it's got the A to Ds, the D to As, the anti-alias filters, the IQ modulator, and the PLL, just in one piece of silicon. So if we now move on to what the development environment, this is Vivado. Next slide. Yep. This is the Vivado, which is the Xilinx development platform. This is a configuration screen for the ARM device. As you can see, you configure how many I/O you know, whether you want one USB port, two USB ports, SPI, I2C, 1 or 2 gigabit Ethernets, where you want them routed to, because it's either got some default pins that these things are routed to, or it can route them via the FPGA fabric to any pin you want almost on the chip. So it gives you some idea of the complexity of these tools. Next slide, please. This is the actual over the top level of the whole system. The top three boxes are to do with the ARM. The one at the right represents the one core on the ARM. The one in the middle is basically handles all the I/O and everything, and the one at the left does the reset. But the magic one is the one at the bottom right. This is the IP, the intellectual property, which does the entire, or would do the entire new television transmitter. It's all in one little box, which you can then export and other people can use in their projects. So you could implement all the DVB-S encoding and the DPD, etc., all in one little intellectual property blocks, which can then be exported to other people, and they can just include it. They can include it in their own designs. Right, next one. What else can we do with DPD? Well, not only can we correct rather grotty power amplifiers. Next slide. We can start playing with Doherty amplifiers. Now, a Doherty amplifier, this comes from AM broadcast days and is used extensively by the cell phone industry. You actually have two amplifiers, one which operates in class AB, which operates most of the time, and then a second amplifier called the peaking amplifier, which operates in class C, that just operates during the peaks. Now, that is achieved by setting the bias levels on the two devices, and you split the thing with a 90-degree phase shift and then recombine them at the output and then match it to the 50 ohms. Obviously, when you do this, as the second amplifier comes into conduction and starts adding to the effort, there's going to be a kink in the both the phase and the output of response of the amplifier, and that's where the DPD comes in. It can compensate for anything to make it look nice and linear again. So that's one possibility that we could do. The next one, next slide, please. Another possibility is what's called envelope tracking amplifier. Now, power amplifiers, they operate at their most efficient when they've just gone into saturation, which is not really something that we want for what we're doing, but DPD can help us again. The way these envelope tracking amplifiers work is they alter the supply voltage on the PA transistor depending on the amount of drive. So you need to take the magnitude of the signal coming out of the DSP and feed it to a wideband switching power supply that will alter the voltage level depending on the output power, and that way you can significantly improve the efficiencies of your amplifiers. However, interesting idea, but probably a step too far for applications. You know the troubles we have with switch mode power supplies. Well, you can imagine switch mode power supplies that you're modulating with a 4 meg wide signal. So I think we can give up on that idea. Next slide, please. And finally, the other projects I'm working on. Well, I'm working on a 10 gigs DAT transceiver, which uses a 9 gig YIG. That's one of the principal reasons why I decided to have a go at producing SSB, because I didn't think I'd be able to work many people on 10 gig DATV. So I thought, well, I might work a few people more on SSB. Obviously, I'm also working on some transverters for 3.4 and 5.7. I've got my vector analyzer project, which I should imagine will never be completed. I've also been playing with some of these Neo N8M multi-standard receivers. Their output, their 1 point pulse per second output can actually be programmed to produce a 10 megahertz output, but it jitters all over the place. So you need it to control a temperature compensated temperature voltage controlled oscillator with lots and lots of filtering in the feedback loop if you want to use that for a 10 meg. But I thought that might make a quite good 10 meg reference for my 10 gig equipment when I'm out doing amateur TV. And finally, I've had a go at doing a total software implementation of DVB-S and DVB-ST. It doesn't work very well. Well, it doesn't work at all, really. It's hit with the problem that it's the synchronization. It's very, very expensive to, if the sample rate isn't quite correct, to compensate for that in real time in software. But I spent about a month understanding all the mathematics behind the way to decode Reed-Solomon codes, and found quite a good NASA paper on how they did it with the Voyager mission. Interestingly, the code they put on Voyager, they had no way of decoding it when they launched the satellite. They worked on the basis that by the time it got to where it wanted to be, they'd have faster software that could decode these things. And that's it. I've managed to do it exactly. There you are. 210. Thank you very much.
Okay, very briefly, any specific questions for Charles? No.
Never is. Never
no,
are.
no. Well, that's because you're just one step ahead of us, Charles.
There was a comment from Ian about 1.7 meg wide. I think he meant DVB-T2. There's a guy in the States called Ron Economos, W6RZ, or RZ, that's developed an implementation of DVB-T2, based some of it on the DVB-S2 stuff I did. He's taken it and put a heck of a lot of work in it. It only runs on GNU radio, but it's a start. I'm not going to bother trying to do this myself, because unless there's people that want to receive it, there's no point in implementing it. It's a bit like the DVB-T stuff. Very few people in the UK use it, so I'm really not concentrating on it too much. That's it.
Okay, thank you, Charles, and thank you very much again. And we look forward to hearing from you probably live next year when we're down south.
I might have something working by then.
Okay, Charles, thank you very much.
Cheers.
Bye-bye. Okay, and